Hi, it's Mr. Anderson, and welcome to Biology Essentials video number 4. This is on scientific evidence for evolution. Here's a picture of Charles Darwin much later in life. Charles Darwin was a very meticulous scientist. He gathered copious amounts of data and to show that evolution was true and that his mechanism of natural selection was right. Unfortunately, he didn't have a really good understanding of genetics. DNA obviously was not around back then, but the scientific evidence for evolution some of the things he could have pointed to were fossil record. This is a baleen whale. If you look at the fin of a baleen whale, it almost looks exactly like the bone structure in the human body, which suggests that both the body and the whale have bone structure similar. Or you could look at the rear legs. Why would a whale have rear legs?
She's cutting all over the place. Nope, that's nothing.
And so today what I'm going to talk about is evidence for evolution. So what is evolution again? It's just changes in the gene pool. But specifically here, we're not only talking about microevolution, but macroevolution as well. First, I'm going to talk about three things that were available to Darwin, and he talked about. Number one is biogeography, in other words, where living things are found. I'll talk specifically about the Galapagos dances. Next, he talked about fossils. Example, I'll give you horse evolution over time. Next, homologies, or those are characteristics that organisms have that show common ancestry. I'll talk about both homologous structures and vestigial structures. And then I'm going to talk on a few things that Darwin didn't have available today, namely molecular evidence. DNA is the trump card when it comes to evolution goes. Finally, I'm going to show you how we can use mathematical models to support our models for how evolution actually takes place. So we've got a lot to do, so we better get started. Let's start with where Darwin started on the Galapagos, formulating his ideas. And I've been here as well, and to see these tortoises the first time is pretty amazing. Darwin's idea was that the giant tortoises on the Galapagos had moved from here
Isn't it right parallel?
From the mainland to the Galapagos. And when you looked at the tortoise on Ecuador, it's very similar. There's no predators, and so they're very big. You can see there's clear differences in the size of the tortoises and more in their structure of their shell. Tortoises that come from really barren areas actually have a longer neck and what's called a saddle shape. Versus a dome shape. This is one from the Santa Cruz, and this one's from San Cristobal. Now, why do we just find tortoises there? Well, there was a founding population that actually moved there. Now, before Darwin, most scientists at that time believed in special creation, that God had placed everything specifically on the island where it was. And Darwin, when he went to the Galapagos, he started to see these islands and similarities, but also differences between those. He started to realize that life and where life is found, we call that biogeography, is big evidence for example, South America used to be connected to Australia. We had a certain type of mammal there called marsupial mammals. We had eutherian mammals up here on the top, and when those two came together, there was a war of the mammals. Eutherians did fairly well. Wiped out a lot of the marsupials that were there, but Australia, as it remained adrift, kept those marsupials. So that would be another example of biogeography.
That's alright.
Next, we could look at the fossils. It's surprising how much fossil evidence we actually have, because it's hard to create a fossil.
Well, good question. I tell you this. He's jumping up and one more.
A great example of horse evolution. Through time, horses have gotten larger and larger as their environment is changing.
Is that really
more of a
7-bitch Emily? You
but we can see that growth reflected in the change in fossil record. In other words, the teeth become flatter.
I don't know what.
They have to run faster when they're out on the plains, and so they move from mini digits to just one digit. And so we can see this transition. It's not linear, it's branched. In other words, if we look at horse evolution, there are many dead ends, there are many branch points. But we can see that there's a continuous thread all the way from those first horses to
Services? I don't hear. Yep, that's right
is really good.
I think alone here.
A surprising amount of data on
whale evolution. Well, we have good questions. I didn't challenge this
and
here.
Darwin talked about this as well.
I didn't know here.
In fact, he actually
Something
mentioned this. And
maybe. Actually, a lover. One. Yep, that's all right. What's up? No! Stop attacking, please!
Where your ears
No! No!
And what it suggests is that
Lori,
we share
no!
ancestry.
Don't alone here at once!
There as well.
Technology.
Homology
I think
or
technology
homologous
her
means
here.
that they
Me?
come from the same
What you
ancestry.
want?
So
What
this
are
would be a
teacher?
human arm.
If
This would be a
I
dog
own
leg.
there's a
This
part,
would be a
yes, but
pigeon
who puts you
wing,
there?
and this would be
I find knowledge.
fin of a whale.
Yep,
If you
that's
look at
alright
it,
here,
you could
loser,
definitely,
right?
if you're an engineer, design
Let me
a
see,
wing
let
more
me see.
efficiently than this wing right here. But natural selection started with
Wow,
an organism
cool.
that had the same bone structure.
I think
so it's
alone
used that
here.
bone structure, and it's
It's
manipulated
Chico,
it to
where's
make,
Mo?
to make the
Yep, that's alright
appendage that
here.
we have today. Vestigial structures are another
I don't
thing
know.
that I could talk about briefly.
Right.
Vestigial structures are structures that once had and did something but don't do anything anymore.
It wasn't?
An example would be
You're
goosebumps.
extra
I
frozen
get
yogurt.
goosebumps when I get scared
Well,
or when I
I
get
think
cold,
alone
but I don't have a lot of fur,
and
so
one
it
more.
doesn't make me
You're
large and it doesn't give
me
me
alone. Your travel.
wisdom
I
teeth,
think alone
primitive
here.
tail, all those things are vestigial
After school,
structures, and
our
appendix,
70s,
and they point to an
90s.
ancestor that actually used those, but
Yeah,
it lost them.
what do you want? What
And so
are
anatomy
teacher?
gives us huge pieces
If
of evidence.
I ordered him, you
Evolution.
me?
But the one thing
You
that Darwin
want
didn't
me?
have
What I want?
is DNA.
What are
And
teacher?
so the best way to talk
I
about
ordered
DNA
him,
start
and
is to
you're
talk about the
ordered.
telephone game. If you've ever played the
The
telephone game,
fridge,
essentially
of
what you
course.
do is you start with
Yes, I know. Isn't it great here alone?
phrase. Let's say the fat cat ate
I think
the rat.
alone.
And then this phrase
Yes,
is
we
going to
don't
be
hear
whispered
the fat
to the second
cat
person in line, who will
ate
whisper it to the third person in line.
the rat.
But let's say the
There
third
is a
person in
me
line
here.
we'll call
Yep,
this person
there's
yellow,
the
makes a mistake.
fat
Instead of saying the
car
fat cat ate
ate
the rat, say the fat
the
car ate the rat.
I
Now
think
that's the
alone
message,
here.
that's the DNA. And so when that DNA is
There's a
copied
me.
again, that mutation
That's
is copied again
alright.
as well. So the fat car
That's
ate the
it.
rat.
You like this here alone. I think
Pink
alone here.
does a nice job
What
passing
for
it on,
everyone's
but then
sure?
eventually we get
The
another
fat
mutation.
car
So we get
ate
another
the
mutation.
bat.
And now it's the fat cat.
I am really. I don't know. Everyone
And now
is
the
a great
fat car ate the bat, and
Plus,
finally the
so
car
much here
car
alone.
ate the bat. So when
The
you get to
far
the
car
end, the DNA
ate
is very similar,
bat.
but it's changed a
There's
little
a,
bit.
that's
And
right.
each of these
You love
are a
science.
mutation. We could
I
call that the
wouldn't
yellow
go over her
mutation,
school
the
like
red
this in the
mutation,
colors.
and then the
We
purple
have
mutation.
black, red,
And so life
yellow,
started
and purple.
with one strand of DNA.
There's love so much light.
All living
We
things on
have
the planet
another
have that same
4
DNA, but
colors
these
like this.
mutations have
Only
accumulated
one
over
color?
time, and so they tell us a lot about
Thank
who's
you.
related to whom. In other words,
There's
if
what's
you
more
were to just tell me what the message
color.
is, and you had this mutation here in
We have
yellow, but you didn't have the red one,
There's
you could
me
trace
here.
where you were.
One black one, a red one,
And so if
a
Darwin
yellow
had
one,
evidence
a
related to
purple
DNA,
one, a pink one like
he
this.
would have had a
You
better,
like me
an
in a
easier
purple
job
color.
convincing
You ain't getting
So let's talk about some specific
purple.
DNA
Yeah.
evidence.
Yours
An example I'm going to give you here
You're
is the
green
human
here.
FGF2
Alice.
gene. Over the last 10
one.
years, we've
Really,
studied
Newbie?
sequencing huge
You have
genomes.
to celebrate
The genome
everyone,
library is a
Joey.
sequence of all the DNA.
You're
inside
my
the
friend
DNA.
of life.
The one I'm going to look at is
Yep,
one
now
that
I'm
makes
ready.
fibroblasts. So it's helpful in
Can you?
healing of
No?
wounds.
You
So
want
we're
me
going to go
here?
to this website
I
right
have
here.
I haven't met you one day. You're one.
We're going to take a look at this
Yeah,
gene.
right
So this
here.
is the human gene,
I am. You're alone.
FGF2.
There's
It's found on
identity.
chromosome 4,
There's
and
identity.
you can tell like how many
And
base
identity.
pairs. It's 6,000
Your
letters
identity.
long. It tells me
I
where
never learned this
exactly it
school.
is. We've learned
No
so
time
much.
to waste you
We
over,
can actually
Alice.
look at all
You're
the
a
letters in
wonderful
that
sport.
gene.
Oh my
Each
God,
of these
what
red
is
ones
that?
here would be an exon, so not
There's
really
a
part
me.
of it. But again, we've got 6,000
What got in your
letters.
way?
I could look at
You're
the whole
bad.
gene. We've sequenced that, and again, this is in Homo sapien right here. So what we could do is now we could line that up. So this is just like that telephone game. We can line it up next to another organism. We can see how related we are. And so let's see what would be a good one to do. Let's do a platypus. So let's compare that same gene in humans and in a platypus, because we've sequenced the platypus genome as well. And what you'll find is that I can look at similarities. And so this would be between Homo sapien right here. Between us and platypus, we find that there are actually some similarities right here. There's some similarities right here. So we actually share some of these genes with the portions of this gene with the platypus. But if I keep moving down and down and down and down, we find that there's really not that much in common between me and a platypus. But probably way more between me and a platypus, since it's a mammal, than me and, for example, a tree. So let's compare something else. Let's find something that's a little closer to home. Let's try a chimpanzee and compare that gene in us and in a chimpanzee. So let's try that. We're looking at BLAST data, so this is sequenced genome. So now if we look at us and a chimpanzee, you'll find, wow, there's an astounding amount of overlap between us and them. All the way down that gene, there's a huge amount of overlap. And so we can compare that and we can tell who's related to whom, and we can also make these evolutionary relationships a little bit more clear. Okay, and so when you hear a chimpanzee and I have 96% of the same DNA, it's because of this. And humans are going to have 99.9999% of the same DNA, but some of that's going to make each other a little bit different. The last piece of evidence we have is not so much evidence, but it's a way to see how evolution takes place, and that's using population simulation software. And so what we have here is a way to simulate a population. Now remember, let's run this for a second. So this is a population the size of 1,000. We're just looking at one allele here, so we're looking at one gene, and it's two varieties of the gene. And so if we look at this value up here would be my p-value. This right here, let me change it to a different color. This would be my q-value. And then here are going to be my different genotypes. And so if this is, let's say this is the big P is big H, and this is little h, maybe we're looking at Huntington's. Then this would be homozygous dominant, this would be heterozygous, and this is homozygous recessive. And so we could simulate it again, so let me do that for a second. Let's go back and simulate that again. And so chance is going to take over. So we could get a little bit of genetic drift this time, but the nice thing about population simulation software is it allows us to play around with those 5 different things, those 5 things that are required to maintain this equilibrium. So for example, we could play with a bottleneck. So maybe we want to make a bottleneck here from generation 100 to 120, where the population goes from 1,000 down to 10. And let's try to simulate that and see what happens. So now we've got 1,000 in our population, but now it's going to change. We're going to have a bottleneck effect right there. And so we could study how a bottleneck is going to affect the population over time. Or we could look at mutation or migration, or let's try fitness. So let's say if you're homozygous recessive, let's say you have a 50% chance of survival. So we could do a little bit of selection here, and we could run it again. Let's try that again. And now we have a p-value that's going way up, a q-value that's going down, and we have almost the elimination of that homozygous recessive down here. So again, the evidence that Darwin had for natural selection was a ton. The one thing he was missing, though, was what we now have a really good understanding of now. So that's DNA. That's how DNA is passed from generation to generation, and as it does that, it leaves these wonderful footprints that we can track evolution. And so I hope that's helpful.